Okay, so let's start with reversible reactions. So these are reactions which can go in both directions, right? So reversible reactions, they're represented by two arrows, both pointing in opposite directions. Like one is pointing forward, the other one is pointing backwards.
backward.
So there's your reactants, and here are your products. Um, so you can move from reactants to products, but you can also move back from products to reactants, and sometimes you can do both at the same time. So that's what a
Mm.
reversible reaction is: reactions that can go in both directions.
Okay.
So reactions that can go in both forward and backward direction.
Okay.
Forward and backward direction. So do you know any examples of reversible reactions?
Yeah, like if you have a weak acid, then it can be reversible because it doesn't all ionize.
Okay, so that is one, like ethanoic acid. Um, it would ionize, and the ions could actually join back again. The negative and positive ions can connect to each other, and they can join up again. So it could go in both directions, and it's going both in forward and backward directions, pretty much at the same time. That's known as a dynamic equilibrium.
Okay.
So what's a dynamic equilibrium? It's a reaction where the rate of forward reaction and the rate of backward reaction is equal.
Okay.
And remember, it's the rate, the speed of the forward and backward reaction. Rate of
Okay.
forward equals the rate of backward reaction. In a reversible reaction. So rate of forward equals rate of backward reaction, and one everyday example is a closed water bottle. What you would see in a closed water bottle is that if let's say there's this closed container, it has water in it, right?
Mm.
Why doesn't the water evaporate in a bottle that's closed?
And because it can't escape.
But is it evaporating or not?
Yeah, it is.
So molecules are constantly gaining energy, and the top surface molecules are constantly evaporating. So they're constantly evaporating, right? And then what
Yep.
happens? And then what happens?
And then the condensation falls back down.
So eventually they don't have any place to go, so they're going to bump into the walls of the container, and eventually they would lose energy and they would fall
Back
back.
down.
So so H2O liquid would be constantly evaporating into H2O gas,
Mm.
but at the same time it would be constantly turning back into liquid as well. So the reaction is pretty much not going anywhere.
Okay.
So that's a reversible reaction, and you might have noticed that pressure builds up inside the container. Uh, like if you have a water bottle, it's if you open the water bottle, there's some pressure built up because the
Mm.
molecules the molecules are constantly They are constantly evaporating.
Okay.
So then, so that's one example of a
Yeah.
reversible reaction. Now, a reversible reaction could it could shift. I mean, this is known as equilibrium. So, can you make the equilibrium move and favor the? I mean, can you make it move?
Yeah.
I mean, let's
You
say
can make it. You can make it more warm, so evaporate more in the glass.
okay.
Or you can make it colder, so it condenses more.
So that means the equilibrium would start favoring one of the sides. Okay, it's going to
Yeah.
favor the vapors, or
Yeah.
vice versa. You can do the other thing as well. What you could do is you can make it move. That's known as the equilibrium position. You're trying to shift the equilibrium position left or right. Basically, the reaction would be written like this. I mean, not specifically like this. It's usually written like this. And the terms that are used are that you're making the equilibrium position move to the right. Like
Mm.
if you heat it, if you decrease the temperature, it would the equilibrium position would move to the left.
Okay.
And if there are equal quantities of vapor and liquid at the same time, then the equilibrium position would be somewhere in the middle.
Okay.
Okay, is that clear?
Yeah.
So you can move the equilibrium position left or right. Um, but if you're not changing conditions, the equilibrium position would remain fixed. Okay,
Okay.
the quantity of water vapors that are formed, they would not change, because if 10
Okay.
molecules are evaporating at every second, then 10 molecules are also condensing every second, so the net quantity remains exactly
Okay.
exactly the same. Okay, is that clear?
Yep. Yep.
And do you know what the least chattel principle is?
No.
As it's a principle where you can actually predict where the equilibrium would actually move. Okay? I mean, just like we just did, like we predicted where the equilibrium would move, right? Whether it would
Okay.
shift to the right or to the left. So the principle
Okay.
is used to do exactly that.
Okay.
Uh, what the principle states is that the equilibrium would try to oppose any change that's introduced to the system. So any change that's introduced to the
Okay.
system.
Yeah.
So that's your Lee Shatler principle.
Okay.
Now, I mean, there are three rules to the Lee Shatler principle. The first one, which reaction would be favored if you increase temperature?
Um. So we're going from liquid to gas.
Which is evaporation, right?
Mm.
So it's going to go in the forward direction, right?
Yeah.
Uh, so what is the forward reaction? It is evaporation, but is it an endothermic process or an exothermic process?
Um. Yeah, an endothermic process.
So what happens is when you increase temperature, I mean the reason I'm not using the term evaporation is because you can't really use the term evaporation for every reaction.
Right.
So we're going to focus on this. Endothermic reaction is favored, right? So the endothermic reaction is going to be favored, which in the
Okay.
above case
Evaporation.
is evaporation. Because the reaction that needs energy is going to happen at a faster rate if you increase temperature, because you're giving it energy, right?
Yeah.
And number to what would happen if you decrease temperature.
Exothermic reaction.
So vice versa, the opposite would happen, exothermic reaction. Exothermic reaction is favored. So you have the so just remember this is the first rule. And you can generalize this rule to almost every reaction. For example, you have this reaction happening. So there is N2 reacting with 3H2 and it's in equilibrium with 2NH3. And the delta H is negative. Now remember the delta H that's given, it's
Mm.
usually given for the forward reaction.
Okay.
Not usually, it's always given for the forward reaction. So
Okay.
when they say that delta H is negative, that means it's exothermic. That means the forward reaction is the one that's exothermic. TK, is that
I
is
don't
that
get
correct?
that.
Hmm?
I don't get that.
Do you know what I mean enthalpy change? Enthalpy change is the energy change for the reaction, right?
Yeah.
And they're saying that it's negative. That means it's exothermic.
Oh, okay. Okay. Yeah. Yeah. Okay.
So so remember the enthalpy change that's provided for a reaction, it's always given for the forward reaction, not the reverse. The
Yeah. Okay.
reverse is actually the opposite of the forward.
Okay.
So if this had been positive, then the forward would have been the one that would be endothermic.
Okay.
So which one is exo, which one is endo? It varies from reaction to reaction.
Reaction.
So
Okay.
tell me what would happen if I decrease temperature?
If you decrease temperature, then an exothermic reaction will form.
So exothermic is favored. You use the word favored,
Okay. Favored. Okay. Oh, okay. Favored.
which in this case is the forward reaction, right?
Yes.
Or you can say the equilibrium shifts to the right. So you can say equilibrium position shifts to the right.
Okay.
It shifts to the right, right? So that's one example. If they had told you that you're increasing temperature, then which reaction would be favored? The endothermic one, which is the backward one,
Mm.
right?
Mm.
So that's the first point. The second point and the third rule for the Lee-Shatler principle is about pressure.
Okay.
So the second and the third rule are for not the second, the third and the fourth rule. So rule number three: increased pressure, less gas moles side is favored. And vice versa, if you rule number four is the opposite. If you decrease pressure, then more gas moles side is favored.
Okay.
As another thing is, how does that make sense? So let's look at the container that contained your liquid water, right? So it had your H2O liquid,
Yeah. Okay.
which was constantly evaporating, and it was evaporating to form these gas molecules, right?
Mm.
But now the thing is, you have a piston on top. Like you have a movable piston,
mm,
that could that could be pushed downwards or it could be moved upwards as well. So here's your movable piston, right?
okay.
What does it mean if I want to increase pressure? What
You
am I
push it
supposed
down.
so I'm supposed to push it down, right? So
Mm,
I'm trying to increase pressure.
mm.
So what's going to happen? Would there be more gas formed or less gas? Like if I start pushing the piston down,
Less found.
so I'm pushing it down, right?
Mm,
So why would there be less formed?
because it's pushing down onto the liquid, so the liquid doesn't release as much gas because it's getting pushed down from the top.
Oh, I mean, and plus there's no room left, right?
Yeah.
And the amount of gas would become lesser and lesser as if I keep pushing it down. Nothing would happen. Liquids are incompressible, but the gases are
Mm,
compressible. So if I keep pushing it down, uh, eventually what would happen is there's not going to be any gas, right?
yeah. Okay.
So if you increase pressure, less gas. I mean, what this means is that less gas mode side is favored. That means uh, the side where there is less gas, that's going to be favored.
Okay.
And what's going to happen if I decrease pressure? That means I'm going to pull the piston upwards, right?
Yeah.
So if I all of a sudden decide to decrease pressure,
Mm,
and the piston is now somewhere right at the top, right?
mm,
Now what's going to happen? Automatically, there's going to be more evaporation, a lot more evaporation, because there's a lot of room now
okay.
for the gas to form. So what's going to happen?
Mm,
More gas is going to form.
okay.
Okay, so in this case, and remember, if a mixture doesn't have gases, then this rule doesn't apply. It only counts the gas moles.
Okay.
So which side has more gas moles, the forward or the backward?
The forward.
So there's 1 mole of gas there, right?
Yeah.
And in the backward there is no gas, so that's
Yeah.
0 moles
Zero
of
moles.
gas.
Yeah.
So what's going to happen is if I decrease pressure, it's going to move forward. More gas is going to be produced,
Okay.
right?
Yeah.
So if I decrease pressure, more gas would be produced. Vice versa, if I increase pressure,
Mm,
less gas moles would be produced.
okay.
I mean, this is basically increased pressure.
Okay.
So less gas is going to be produced. Okay, is that clear?
Okay. Yeah.
So remember these two rules.
Okay.
Now the last point is, and let's sum that up in a single point. So the fifth point is that if I increase concentration, and remember the concentration, we're talking about concentration, not the number of moles. So if I increase
Okay.
concentration of increase or decrease, I mean it could be the opposite as well, or decrease. So if I increase concentration of
Mm,
a reactant,
yeah.
or it could be the product as well.
Mm,
Okay, so if I increase the concentration of a reactant, equilibrium would oppose that.
okay.
Equilibrium would favor that reaction that decreases the concentration of the reactant. That does the opposite.
Okay.
Which means in this case, if I increase concentration of a reactant, equilibrium is going to try and decrease the concentration of a reactant, right? So the
Mm.
so the concept behind that is, what if I look at this container? Let's say it's at equilibrium. I'm not touching the piston now, and all of a sudden, I mean, there's this reaction happening, right?
Mm.
Water liquid constantly changing into water gas, right? And coming back.
Mm.
So all of a sudden, I go in and I remove all the water vapors.
Okay.
So so what am I doing? I'm removing the water vapors, right?
Yeah.
What would the equilibrium do, or what's going to happen now?
Um.
I mean,
So
I went inside. I removed all the
mm,
water vapors
yes,
in
it's
one
gonna be
go.
will be equal then.
No, listen, I've removed the water vapors, okay, and I've
Mm.
now I'm out of the container. I've done my job. What's going to
Okay.
happen now? I mean, which
You
reaction
g-
thing is not going to happen? Which one would still be happening?
it's gonna change the gas afterwards anyway, isn't it?
Yeah,
Are you on about the yeah? So but okay, so it can't go from gas to liquid. We're gonna go from liquid to gas.
because there is no gas, right?
Yeah. Yeah.
So basically, what would happen? Evaporation would happen,
Mm.
and the water molecules would be reformed, right? There would be evaporation, and basically condensation would start again as well.
Yeah. Okay.
So what happened? It did the opposite. I removed the water vapors. It
Mm.
made them again.
Okay. Then it will go the opposite way.
And similarly, if I go in and I add more water vapors, right?
Mm.
All of a sudden, I've added a tons of more water vapors. What would the equilibrium do?
Um. Then it'll go more from gas to liquid.
So condensation would kind of speed up, right?
Yeah.
Because there's so many water vapors. So the speed of condensation would be lesser.
Mm.
And if condensation speeds up, then the amount of water molecules would start to decrease,
Yeah.
right?
Mm.
So so if I try to decrease something, it tries to make it again.
Okay.
If I try to increase something, it tries to decrease it.
Okay.
Okay, so that's what's happening here. So we're gonna try
Okay.
and do a worksheet now. And let me find. I think I had a worksheet somewhere. One second. There's a rate worksheet. Equilibria. One second.
Mm.
First question is for the reaction below. Which change would cause the equilibrium to shift to the right? I mean, you want the equilibrium to kind of move to the right, right?
Okay. Yeah. So A would because we dihydrogen sulfide that 2H2S, right?
Yeah.
That would make it go the right more.
Like if you, what you're saying is, if
Because
you,
there'd be less moles here and be more moles on the right.
no, you're decreasing it, right?
Mm.
You're you're decreasing the concentration. Think carefully.
Yeah.
What would the equilibrium do?
Oh no, then it will go that way actually. Then it will go to the left.
Because it's going to try and do the opposite. It's going to try and increase the concentration, right?
Yeah.
So
Uh,
it's going to go make it move to the left.
okay.
Not that one.
Okay. Um.
What's the other option? Increase the pressure on the system. If you,
I think it's gonna be so if you increase the pressure, then that means the less is formed, so more gets formed.
less gas moles, right?
Yeah.
Which side is less gas?
The one on the right, the one on the right has more because it got 4 moles or five
I
and
mean,
one
in
left is
total,
only 3.
okay, in total it has 5 moles, right?
Yeah.
This in total has 3 moles, right?
Yeah.
So it's gonna go in the backward direction, right?
Mm.
I said then you have forget temperature for a second because we don't know which one is endo or exo. Increase the concentration of carbon disulfide.
Okay. Carbon dioxide. So that'll make it carbon dioxide. That'll make the one on the right. So then that means there's more on the right. So I'll try and equal it out by going to the left.
No, the question is one second.
So, 'cause there'll be more moles on the right then. So they'll
Yeah.
try and go. So they'll try to go to the left to try and equal it out.
Okay, that's fine. So that's obviously not the answer.
Yeah.
And what about the next one? If you decrease the concentration of methane, you're decreasing the concentration of methane.
Yeah. Okay. So if you do that, then it'll try and put more on that side again to get more. So then it'll go to the left more.
Okay. So
So that
more
means it must
methane.
be increase the temperature.
So it's going to be increase the temperature, right?
Yeah.
But you can't really tell because he didn't tell us which one was endo, which one was exo. I mean, the question is kind of incomplete. Um, Move to the next one. What would happen to the position of the equilibrium when the following changes are made to the equilibrium system below? If you add sulfur dioxide to the system, what's going to happen? Sulfur
Yeah.
dioxide
Then
is
it's gonna go. Equilibrium is gonna move to the left,
okay. So this one is going to make it move to the left, right?
and then the second one's gonna make it move to the left, and the third one's gonna make it move to the left as well.
So all are heading to the left.
Yeah.
What about the next one? What would happen to the position of the equilibrium when the following changes are made to the reaction below?
It's gonna move to the right for A. On B, it's going to um, it's gonna go to the right.
This one?
No, 'cause it's increasing. It's gonna go to the left.
More gas, less gas. What's going to happen?
It's gonna be less gas.
So it's going to be
The
it's
goal
going to be
is so it's gonna go to the right. We're gonna try and get more gas on the right.
isn't it going to go towards the less gas side?
Yeah, and the less gas. The only one side which has gas.
I mean, so there's 1 mole of gas here,
Hmm?
and there
And
is
no zero more on the other side.
so which one is the less
Oh,
gas?
oh, oh yeah. So we're gonna go to the one on the left. So it's gonna go to the one on the left.
Okay, so this is where there is no gas.
Okay.
When the volume of the following mixture of gases is increased, what will be the effect of the equilibrium position? If you increase volume, what happens?
Mm, Uh, then nothing changes because everything increases. Oh no. Wait, what? Uh, oh wait. So there's five more on the left and there's four more on the right. They're gonna go to the right to try and get more over there to equal out the five on the left.
No, I didn't get it. See, you're increasing volume, right?
Hmm?
So that's like low pressure.
Yeah.
So there's more gas to be
Exact.
formed.
Yeah. So you want to go to the side with less gas, right?
No, you want to go to the side with more gas. I mean, you have more volume now.
Hmm.
So if you have more volume,
Okay.
more gas would be produced.
Okay. So then, if you go to the side with more gas, then that'll give it even more gas, won't it?
I mean, that's what you want here.
Oh, okay. And then it's gonna go to the one on the left, where it's got five moles of gas.
Okay, because you're increasing the volume, right?
Hmm.
So you have more volume, more gases could be formed.
Okay.
Okay, is that clear?
Yeah. Okay.
Acha, the effect of decreasing the volume of the container, that's basically you increasing pressure, right?
Hmm. It's gonna go to the side which has less gas this time.
Yeah, so what's the first one?
It's gonna go to the right, and the second one's gonna go to the left, and the third one
No, the first one
it's
is going
going
to
to
go
go
to
to the
the
left.
left.
Yeah. And the second one is going to go to the right, and then the last one is gonna go to the left. Sorry, the right.
The second one is going to go to the right.
Yeah, and the third one is gonna go to the right as well.
Yeah. Next one is predict the effect of decreasing the temperature on the position of the following equilibria. Now
Yeah.
he's given you endo and exo. This is plus.
Okay. So if it's plus, then that means it's gonna be endothermic, right? But if it's giving off energy, then yeah, so it's gonna be endothermic. Wait, no, exothermic gives off energy, right?
Yes.
So it's exothermic, and then if you decrease the temperature, then that's gonna make it less exothermic, right? And then wait, what? How will that make a difference on if it's exothermic?
Which one?
I'm not sure how to do this on.
Uh, See, the forward is endo, right?
Hmm?
And the backward is
Exo.
it's going to be exo. So you're decreasing temperature. Which one should be favored?
Sorry?
You're decreasing temperature. So which one is going to be favored?
Uh, then it's gonna go more towards the the endothermic side because you can have more endothermic.
If you decrease temperature, it's going to favor the exothermic reaction
Why?
because that's what we learned. Just one second. Where's the where's the endo exo part? Like the evaporation thing. If you decrease temperature, which reaction would be favored? Condensation or evaporation?
Condensation.
And that's the exothermic reaction, right?
Okay, okay, yeah, okay, okay. As it gets colder, it gives more exothermic. Okay,
Yeah.
okay.
So it's going
So
to
on
be
that one, it's gonna go to the left.
left. Oh, what about this one? This one is also, I think,
You're
endothermic.
going to go to the left. You're gonna go to the left as well.
And this one,
That's gonna go to the right.
I think it's going to go to the right. And the next one is what is these are solution. We're done with the. Are we done with the worksheet? I think we're done with the worksheet.
Okay,
Okay, so next time we'll do past papers now. But I'll probably I'm going to send you some questions right now. Um,
okay,
Let me see if let's try and do these. One second. There's another Lee Shatler principle worksheet somewhere. Okay, let's try and do A levels. I mean, it's still Lee Shatler principle, right? Uh, so the question is that there are two reactions that are going on in the swimming pool, right? The first
hmm,
one and the second one.
okay,
The first one is an equilibrium reaction. It's a reversible reaction, right?
okay,
So
yeah, yeah.
which method would maintain the highest concentration of HOCl? You want more.
Uh,
You want more HOCl.
okay, so you want to be favored to the right.
Yeah. So the first one is
Okay,
you acidify the pool water.
okay.
So
Uh,
what would acid do?
as it will make them be more less OH ion, less OH minus ions compared to OH H ions.
Yeah.
So then that's gonna make it go to the left.
If there's less OH ions,
Yeah. Okay, let's say ions, and it's gonna go make it to the right.
yeah, it's going to try and increase OH ions, right?
Yeah, incorrect. So it gets equal. Yeah.
So you get more HOCl, right?
Hmm.
So the first one is the correct option
Okay.
because you wanted the highest concentration of HOCl.
Okay.
What would happen if you add chloride ions?
It's gonna go.
Like the first one,
It,
would it matter to the first one if you add Cl minus one ions?
no, because it's same amount on either side.
And this is not a reversible reaction, so nothing would happen over here.
Yeah.
Add a solution of hydroxide ions. If you add more hydroxide ions, where would the equilibrium shift?
It's gonna go to the left because it wants to get more on the left.
ठीक है, and if you bubble air through water, that means oxygen. Again, this is
Mm,
not a reversible reaction. It's not going to go anywhere.
okay.
I said this one. Which statements are correct about this? Increasing the pressure increases the yield of SO3. Does it?
Okay.
If you increase pressure,
Because if you increase pressure, they're gonna be, they're gonna so increase pressure, so there's gonna be less gas formed. So it prefers to side with more gas, prefers to side with less gas, right?
yeah.
So it's gonna be, yeah, it's gonna be, one is correct.
ठीक है, that's correct. What about increasing the
Okay.
temperature lowers the value of Kp? Forget Kp. Not. What does a catalyst do? If you add a catalyst, what does it do? We didn't study this, but
It will
what?
speed up speed it up without getting used up itself.
No, it's going to speed up the reaction, right?
Yeah.
So what would happen to the equilibrium position?
Uh, it'll go more towards the, it's getting speed up, it'll go more to the right because it's going quicker.
No, because it's
It'll go more to the left because short amount of time on the left.
no. The thing is that if you add a catalyst, both the forward and the backward reaction are speeded up almost at the same rate.
Oh, okay.
So
Okay.
that's why the equilibrium stays wherever it was.
Okay.
So catalyst doesn't really alter the position of the equilibrium.
Okay.
So which statement about reversible reactions are correct?
Um, increasing concentration of a reaction always increases the concentration of the product. Um, the concentration of the product. A one.
Konsa, what about one?
Sorry,
Nee, what about one?
that's the one that's correct.
Okay, that's fine. But I mean, this question, multiple statements can be correct. What about the second one?
Um, no, because if it's endothermic and you had heat to it, then it's not the same as if you have heat and exothermic.
So one thing we didn't study here is don't confuse a rate with equilibrium. See, the thing is that when we say that one reaction is favored, right?
Hmm.
That doesn't mean that it speeds up. Uh,
Okay.
what it just means is that one of the reaction is faster compared to the other ones. Maybe both of them are slowing down, or maybe both of them are speeding up. But
Okay.
one of them, in relative terms, is it's faster compared to the other one. Do you get my point?
Okay. Yeah.
Like if you cool this down,
Hmm.
maybe both
Everything's
reaction
gonna guess.
maybe both
Right.
reactions slow down, right?
Hmm. Hmm.
But the
But
equilibrium is going to favor the condensation. I mean, this would still be faster compared to this one.
okay.
So the thing is, don't confuse equilibrium with rate. Rate is
Okay.
something totally different. And
Okay.
and when you talk about equilibrium and when you talk about one reaction being faster than the other one, you're
Hmm.
just talking about them in relative terms.
Okay.
Okay? Maybe both reactions are speeding up, or
Okay.
maybe both reactions are slowing down, but one is faster compared to the other one.
Okay.
Okay? So ठीक है, we can continue with this worksheet then tomorrow then.
Okay. Thank you. I love it.
Okay, take care. Allah Hafiz.